This is the fourth and final part of a review of limits and continuity. If you have not seen parts 1 through 3, you can either click the link that appears in the upper right hand corner, or you can find the links in the description. In this video, I will show you how to find the values of a and b that make f of x continuous. How do you show that f is continuous at c using the definition of continuity? You have to show that the limit as x approaches c from the right of f of x equals the limit as x approaches c from the left of f of x, which equals the value of f at c. For number 17, we have this piecewise function that has an a and a b in it. A and b represent real numbers. The second and third pieces are continuous by themselves. A is a constant, so that's obviously continuous. Bx squared, that's a polynomial, so that's going to be continuous. This rational function does have a discontinuity in it, but we know exactly what it is. There's a vertical asymptote at x equals 2. So what I'm trying to convince you of is that the only value of x that we have to worry about, the only location of a discontinuity, would be at the value of x equals 2. That's where we switch from one piece to another. It all happens at x equals 2, and also that's the only discontinuity in the rational part of it. So if f of x is continuous at x equals 2, it is continuous everywhere. So really, we just need to find the values of a and b that will make f of x continuous at x equals 2. According to the definition of continuity, f of x will only be continuous at 2 if the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right, which in turn equals the value of f at 2. So let's find an expression for each one of these, and then we can set any of them equal to the other to solve for a and b. Let's start with the limit as x approaches 2 from the left. From the left, we're talking about values of x that are less than 2. So that means we will use this piece of the piecewise function. So x squared minus 4 over x minus 2. We need to find the limit of this expression as x approaches 2 from the left. Let's factor this. So we have the limit as x approaches 2 from the left of x plus 2 times x minus 2 all over x minus 2. Of course, we now notice that we have the same factor in the numerator and the denominator. Canceling these out will not change the value of the limit. So now we have the limit as x approaches 2 from the left of simply x plus 2. This can be evaluated by direct substitution. Plugging in 2 for x, we have 2 plus 2, which is equal to 4. So that is our expression for the limit as x approaches 2 from the left. Now let's find an expression for the limit as x approaches 2 from the right. Well, from the right of 2, we're talking about values of x that are greater than 2. So the third piece of the piecewise function will apply. So we need to find the limit as x approaches 2 from the right of bx squared. But this limit can be evaluated by direct substitution. If we plug in 2 for x, we get b times 2 squared, which is 4b. So that's it. This is our expression for the limit as x approaches 2 from the right. Now let's find an expression for the third piece of the definition of continuity. Let's find the value of f at 2. Well, f at 2 means x equals 2, and that is a according to this piecewise function. So f at 2 is simply a. So this is our third expression. And according to the definition of continuity, all three of these expressions are equal. So we can set them equal to each other in any way we want, in any order that we want, in order to solve for a and b. So the easiest thing to do is to start by setting a equal to 4. Those are going to be equal. So a is equal to 4, and kabam! Just like that, we have found the value of one of the variables. Now all we have to do is find the value of b. Let's find b by setting 4b equal to 4, because these should also be equal. So 4b should also equal 4, and dividing both sides by 4, we get b is equal to 1. So that's how you find the values of a and b that make the function continuous. I recommend that you always start off by writing out the definition of continuity like this.